These are the 2.1 part 2 notes, and we're going to continue with some function rules today. We're going to be looking at the domain of the function, and we're also going to be looking at function operations. Now, the domain of the function is something that we've got to review. There are three functions that we're going to assume that you already know, and we're just going to touch on them quickly to figure out what the domain is. Now, what is the domain? The domain is the idea of what are the x values that we can plug into a function and we can get a y value out. So there are a lot of functions where if you plug in an x value, it's not going to work for whatever reason. And I'm going to explain those in the two examples that we have where we have exclusions. There are some functions where no matter what x value you plug in, doesn't matter if it's 1, doesn't matter if it's a million, doesn't matter if it's rational like pi, you get a number. It doesn't matter if it's negative, anything like that. As long as you plug in some value, you will get a y value out and it will remain a function. There are other functions where if you plug an x value in, the input's just not going to work. You plug it in, it can't function. It's kind of like this idea that, you know, there are some things in like to go back to the vending machine. If you put like quarters, dimes, nickels, etc. in the vending machine, it'll work just fine, but like you'll see how it says only accepts 1s, 5s, 10s, and 20s. If you put a $50 or a $100 bill in a vending machine, it doesn't work anymore. Those inputs will not give you an output of any food whatsoever. So there are some times that we have these limits where it can accept some things, but it can't accept the others in order to operate. Now, the three functions that you need to know the domain of are polynomials, rationals, and radicals. These are pretty easy to keep straight as long as we know what we're looking at. This is something students have historically struggled with. This really is kind of like a hard, fast set of rules that you just kind of need to memorize or understand. I can go into the detail of why each one is, and I'm going to. However, even if the detail is confusing to you, you can remember the patterns of if it's a rational function, if it's a radical function, if it's a polynomial, etc. Our first example here is a polynomial, and we're going to be looking at these all the time. With polynomial functions, your domain is always all real numbers. And there's a number of ways that we can write this and be correct. I am not going to be a stickler with how you write your domains. My biggest concern is that you get your domains correct. So if you tell me, if you write out this, all real numbers is the domain for a polynomial, you'll get full credit. You can also write like this, where you do negative infinity to infinity. You can do what our book would do, which would be all values of x. Or you can also just write this, an R with two lines. So as opposed to putting just an R down, you make an R with like two of those backbones, and that means all real numbers as well. So when you write that down, you're telling me no matter what x you plug in, that x is going to give you an output from the function. And that's always the case with polynomials. Polynomials are always all real numbers. Polynomials aren't our only functions that are all real numbers, but they are one of the biggest ones, and if you ever see a polynomial, it is just all real numbers. Very, very easy domain. Here we have a rational function. And I know it's a rational because I've got a variable in the denominator. And when I have a variable in the denominator, what I do is I say to myself, okay, we learned this all the way back in like 3rd, 4th grade. If you've got 3 divided by 0, that does not exist. We can't divide by 0. That's like saying, okay, take this number and divide it up into 0 parts. It's impossible to divide something up into 0 parts. That doesn't make sense. So what I say is, okay, I'm going to set my denominator equal to 0. So I set x squared minus 4 equal to 0. And then I solve. So I get x squared is equal to 4. X is equal to the positive negative square root of 4. And then x is equal to positive negative 2. Oh, that is a weird way to write that. So x is equal to positive negative 2. So to figure out when you have a rational function, what your domain is, you figure out what makes your denominator equal to 0. And then these values here, this x is equal to positive negative 2, those are the values that my function can't be. So I could say all values of x, where x cannot be equal to positive negative 2. You could go through and do what you guys might have learned in Algebra 2 last year of saying negative infinity until negative 2, union negative 2 to 2, union 2 to infinity. That's one way. I think this way up here is the easiest way of writing it, of the x is all values except where x cannot be equal to positive negative 2. That's commonly how you're going to see my domain written. That's the way the book goes into writing your domain. That's called set builder notation. This down here, this negative infinity to negative 2, negative 2 to 2, 2 to infinity. That's probably what you learned a lot of in Algebra 2. That's called interval notation. You could also just write out all real numbers except where x cannot be equal to positive negative 2. This is kind of like the mathematician's slang. This is our way of saying that, okay, all values of x are going to work except for the values of positive negative 2. But somehow you have to indicate to me that in this function, if I plugged positive or negative 2 into that x squared value, I would end up with 0 in the denominator. And therefore, this function cannot work. So that is how I figure out my domain for that function. The last one is a radical function. And with a radical function, your square root always has to be greater than or equal to 0 because the square root of a negative number is equal to something imaginary. And we are not dealing with imaginary numbers here when defining our domain. So what I want to do is I just take the interior of my square root, that 4 minus 3t, and I set it greater than or equal to 0. And it's important that you have the greater than or equal to 0 there because we can still take the square root of 0. It's 0. 4 is greater than or equal to 3t. 4/3 is greater than or equal to t. So what I can say here is that this is going to be all values of x as long as, or t, sorry, this is a t function, not an x function, all values of t, where t is less than or equal to 4/3. I can also say that it would be from negative infinity until 4/3. I can do this interval notation. This would also be an acceptable answer. I could say all real numbers as long as t is less than or equal to 4/3. I could also just write out as a sentence the domain of the function the square root of 4 minus 3t is all values as long as the values of t are less than 4/3. That's a lot of work. These mathematical definitions that we have here, this set builder notation, this interval notation, and this like mathematician slang, all still tell me that exact same thing as that sentence that I said, and that lets me know what my domain is. You're telling me that as long as I'm plugging in a number less than 4/3, I will get an answer in this radical function that is greater than or equal to 0, and therefore you can perform this operation. And those are your three rules. All polynomials are always real numbers. For rational functions, you set your denominator equal to 0, and it's your values that make it equal to 0 can't be in your function. And then for radicals, you set the inside of your radical greater than or equal to 0, and that will tell you whether or not you whether or not it can be plugged into the function. So I've got a U-try, which is a little bit different. These are old notes, but I'm still going to work with them. Back in the day, I would have had you perform these. If you want to take a second and pause on the notes and see if you can figure out the answers, and then play the notes and see if you have the answers correctly. I'm just going to quickly run through the answers. I'm not going to go through the explanation again. But A is a polynomial, so therefore it's all real numbers. I use a lot of mathematician slang. I'm cool and hip that way. For B, I say rational, so I need to set my denominator equal to 0. I get t squared is equal to -7, and this one's a little bit tricky because if I take the positive negative square root of -7, I would get an imaginary number that doesn't exist. So this one actually ends up being all real numbers as well. This is a special case. If you guessed all real numbers on that, you got lucky, but here that's actually all real numbers because there's not a single number on the planet that's going to make that denominator not equal to 0. Then finally, for C, I've got a radical function. I say 6 plus 3n greater than or equal to 0. 3n greater than or equal to negative 6. N greater than or equal to negative 2. So it's all real numbers where n is greater than or equal to negative 2. And there you go. There's my mathematician slang answer. And there's plenty of ways you can answer that, but again, I go with the mathematician slang. All right, function operations. You've got 4 operations here. You've got the sum of 2 functions, you've got the difference of 2 functions, and the product of 2 functions. What this means, like for the sum of 2 functions, you just combine like terms. For the difference of functions, you combine like terms. For the products, you're going to expand, you're going to multiply. Treat it like it's a polynomial multiplication or however you need to do it. And then quotient, you're doing division. Now you've got domain rules. They're kind of shown up here as well. The domain of f plus g of x, f minus g of x, and f times g of x are all the numbers that are in both the domain of f of x and g of x. I think that's going to be easier to understand once we get to the examples. Just like the domain of f over g of x consists of all the numbers that are both in the domain of f of x and g of x, as long as g of x also does not equal 0. So let's go ahead and look at doing these functions. I know that the domain probably doesn't make a lot of sense right now. I think this is something that is much more straightforward when we look at our examples. So we've got 2 functions here. I start off on easy functions for the first couple examples. We've got x squared plus 9, and we've got 3x plus 5. F of x plus g of x, that's just saying x squared plus 9 plus 3x plus 5. This is just combining like terms. This is really straightforward. This is going to become x squared plus 3x plus 14. There's nothing more. It wants us to list its domain. F of x is all real numbers. G of x is all real numbers. So that means both of these have all real numbers. When I add them together, my domain is just going to be all real numbers as well. So polynomials, always really easy, always really straightforward. You gotta love working with polynomials. It makes your life a lot easier. So here I see that I'm adding 2 polynomials together. My result's a polynomial, and therefore its domain is all real numbers. G of x minus f of x, I have to be careful with my order. I've got 3x plus 5 minus x squared plus 9. I get 3x plus 5. I've got to distribute this like it's a negative 1 minus x squared minus 9. I get negative x squared plus 3x minus 4. And again, this is subtraction. It's polynomials. They started out as all real numbers, therefore they stop as all real numbers. Same function, so I still know that their domains for both of these are all real numbers. I've got f times g of x, so that means I'm going to multiply these out. X squared plus 9 times 3x plus 5. I distribute everything. I expand these out, so that becomes 3x cubed plus 5x squared plus 27x plus 45. And again, I'm multiplying these out. I had 2 all real numbers, so my final domain is all real numbers as well. F over g of x, this is as simple as saying, all right, I've got x squared plus 9 over 3x plus 5. It wants me to figure out what the domain is here. This is where it gets a little bit trickier because notice now that I've done this, I have a denominator. But that's not too bad. This is really straightforward because again, it's just like the old denominator rules. I set 3x plus 5 equal to 0. I get 3x is equal to negative 5. And I get x is equal to negative 5/3. So this one, my domain, is going to be all real numbers where x cannot be equal to negative 5/3. On my homework, it would appear like this. All values of x where x can't be equal to negative 5/3. Both of these are the same thing, so I'll actually get rid of my mathematician slang. and I'll just stick with the more official stuff I use on homeworks. And this would be my answer here. I'm telling you my domain, I'm telling you my function. Again, if I do division, if I put two functions together by dividing them, I have to ask myself, what is this new denominator? Because this new denominator still can't be equal to 0. It's just like a rational function. Anything that gives you 0 on the bottom of a fraction is a bad thing. It does not do us well. So I have to stop and ask myself, do I have a rational function? Do I have a variable in my denominator? And if so, when does it equal 0? Because that's not going to work for this. All right. So again, I've got some U-tries here. If you want to pause the notes and go ahead and make some attempts, I made these tougher than my examples. My examples were just quick polynomials. These are a little bit trickier because they're actually rational functions. Takes a little bit of time. So if you want to pause the notes right now, take a second, see if you can figure them out, and then check yourself back against what I do. If you're completely wrong, that's okay, but watch what I do, see if you can pick up where your mistake was versus mine, and copy down the work. If you're confused as to where you're not sure why you made a mistake or where it came from, talk to me during class tomorrow. That's the reason why I'm doing these video notes, is so that way you can spend more time figuring out what you already know here, and then you can ask me questions in class. I already know, I see here that it says list the domain. So I'm going to go through, I'm going to identify the fact that this one has a denominator. Its domain is going to be x cannot be equal to -2. Because when I set x plus 2 equal to 0, I get x is equal to -2. Just like over here, I'm going to get x can't be equal to +1. I set x minus 1 equal to 0, I get x is equal to 1. X can't be equal to 1 in that domain. So I've got those two domain rules. And now I'm going to do f of x plus g of x. Well, these are tougher, and this is why I said they're tougher. So I've got x over x minus 1 plus 1 over x plus 2. This is actually more complicated because these are rational functions, and as rational functions, I still have to treat them as fractions. So that means I still need a common denominator, so I'm still going to have to multiply x plus 2 over x plus 2. Just like I'll have to do x minus 1 over x minus 1. I get x times x plus 2 over x plus 2 times x minus 1 plus x minus 1 over x plus 2 times x minus 1. That becomes x squared plus 2x. All over x squared plus x minus 2 plus x minus 1 over x squared plus x minus 2. And then so I end up with x squared plus 3x minus 1 all over x squared plus x minus 2. And in this case, again, my domains were different from the beginning. I had a domain up here of x cannot be equal to -2, and here of x can't be equal to 1. So here, my domain is what they have in common. So this is going to be all values of x, where x can't be equal to -2, and x can't be equal to 1. I'm just saying that in one of my functions, x can be equal to -2, and my other function, x can be equal to 1. So when I put these two functions together, it can't be either of these values as well. Even if this one is a little bit easier in the fact that you can see if you moved your denominator, or you set your denominator, in this case, equal to 0, you would get those same results. So that's how I go about that one. F minus g of x, again, it's the same thing. So I've got that 1 over x plus 2 minus x over x minus 1. This case is a little bit easier because I've already figured out what my common denominators are and what they look like with those common denominators. So now I've got x minus 1 over x squared plus x minus 2 minus x squared plus 2x over x squared plus x minus 2. Now, this negative only gets distributed to the numerator when I subtract, so I end up with x minus 1 over x squared plus x minus 2 minus x squared minus 2x all over x squared plus x minus 2. and I get negative x squared minus x minus 1 all over x squared plus x minus 2. And again, these share the same domain, so I have to figure out the numbers that works for both of them. As long as x is not equal to negative 2 and x is not equal to 1, my domain works for me. So once I have the domain for each, I just kind of mash them together. With these function operations, they're easily mashed together to say, all right, these are the two domains. Finally, I've got g times f of x. This one's really straightforward, of saying 1 over x plus 2 times x over x minus 1. And I guess I did that backwards based off how they're ordered, so let me rewrite that in the correct order. So x over x minus 1 times 1 over x plus 2. Really nice thing about fractions is when you multiply them, you multiply across, so I end up with x times 1 over x minus 1 times x plus 2. So I have x over x squared plus x minus 2. And again, I can go through, but at the same time, my domain here is going to be all values of x as long as x is not equal to negative 2 or x is not equal to positive 1, because those were my original domains of these two functions. So since I have those original two domains, since I know that's what it was, I don't have to go any further. B is going to be tricky again because I have this division now. So when you divide fractions, you multiply by the reciprocal. So I've got g over f of x. I've got x over x minus 1 divided by 1 over x plus 2. I divide by the reciprocal, or my favorite little poem that I learned my first year teaching. Dividing fractions is as easy as pi. You flip the second and multiply. So I flip the second fraction upside down. I now have its reciprocal. I multiply by that reciprocal to divide those two fractions. Again, you just multiply across here. So I have x times x plus 2 over x minus 1 times 1. I've got x squared plus 2x all over x minus 1. I already know that my domain will be all values of x, with the exception of x cannot be equal to negative 2 and x cannot be equal to positive 1, as they were already the domain restrictions I found. However, I do have to go through. I have to say that I've got this denominator. I've got to set x minus 1 equal to 0. I get x is equal to 1. We already have that listed in the domain, so this one ended up kind of being non-needed. That would be my domain. The last thing I will show you, because I do want you to see a special case where this might not actually work out, where it's so easy. So I'm going to create a C really quickly. So you can add this in on your notes, find some space. And I'm going to say, I want to know what f of x, f divided by g of x looks like. And what is its domain? So here I've got 1 over x plus 2 divided by x over x minus 1. I've got 1 over x plus 2 times x minus 1 over x. I'm multiplying by the reciprocal. I get x minus 1 over x times x plus 2. So I would have x minus 1 over x squared plus 2x. That would be my final function. My domain here, I already know it's going to be all values of x, where x cannot be equal to negative 2, x cannot be equal to 1, but in this case I'm going to have another special example. I set my x times x plus 2 equal to 0, which means that I've got x is equal to 0 and x plus 2 is equal to 0. We've already found that x plus 2. We already know that x can't be equal to negative 2. But we also have to include in here x can't be equal to 0. Again, let's look, because if I plug in 0 squared plus 2 times 0, that's equal to 0, which is no bueno. That's not good. That's going to give me 0 in my denominator. That's not going to work out for me. So I've got to include that x can't be equal to 0 in my domain value as well. I use the two common domains there, but when I divide, I have to ask myself, is there something new in this denominator? Because if something new pops up in the denominator, if I have a denominator change, if I have a new denominator, I have to stop and ask myself, does this create a new value where x doesn't work? Because if it does, I have to include that in my domain value as well. You guys got a homework assignment tonight. This is not going to be due until the end of the next class, which is either Wednesday or Thursday for you guys. Take your time, work on it. You can start tonight. I kind of advise starting tonight on some of these, especially with the domain. You have an hour-ish, again, to work on it in class. However, you don't want to waste that hour coming in completely blind. If you have an idea of what you're struggling with, what you need help with, I can direct my help a lot more. So I would advise maybe taking 10-15 minutes on this homework tonight, just giving it a quick shot, see what you know, see what you're struggling with, and that way you can come in with questions ready to go. Have a great night, and I'll see you in class.